So we've been constructing the Ito integral and talking about its properties, talking about how we extend it from an integral that gives you a random variable, so the probabilistic analog of a number, to an integral that gives you a process from integrating a process. So the kind of thing that you would need to solve differential equations. But it's about time we actually look at an example and compute such an integral. Now, before we do that, let's just go back to our first year and how we would go about integrating the function, since s to s from 0 to t. So if I ask you to do that, you would say, okay, well, I know that an entire derivative of s is s squared over 2. And therefore, this integral is t squared over 2. So the integral function to function will send the function as goes to s to the function t goes to t squared over 2, right? That's what we know from deterministic calculus. Now, we'd like to do the same thing from a stochastic calculus point of view. So we'd like to integrate in the Ito sense, so integrate against the Brownian, maybe the simplest function of the Brownian I can think of, so just the function that sends the Brownian to itself. So what is the Ito integral of that? And you could say, well, okay, surely it should be bt squared over 2, right? But that cannot be, because we know that the Ito integral sending a process to a process has to give us a continuous martingale, and we also know that bt squared over 2 is not a martingale. In order to make it a martingale, we need to correct it, and we need to add a term minus t over 2. And indeed, this is going to be the answer, not the question. So the answer to the question is that the integral of bs dbs from 0 to t is bt squared over 2 minus t over 2. So we can see immediately that in stochastic, the plain fundamental theorem of calculus is not going to give us the right answer, right? If I just think of 2 here as an analog of 1, then I cannot just use my ideas coming from fundamental theorem of calculus to guess what the answer has to be. So we'll see later on in the course something called Ito formula, which is going to give us the appropriate generalization of the fundamental theorem of calculus that would allow us to guess what this formula has to be. But right now we're going to prove 2. So we're going to compute by hand such a simple looking Ito integral, right? And computing by hand is very difficult. And if you go back to even computing by hand these sorts of integrals, right, and you don't know the fundamental theorem of calculus, then you got to go back to the definition of, say, the Riemann integral or the Lebesgue integral as limits of sums of simple functions, and get this result 1 from the definition. And that's a non-trivial task to start with. That being said, I recommend doing it. You could try that as a warm-up case for the proof that I'm going to do of 2, which uses similar ideas but is harder, obviously, in the stochastic case. Okay, but let's see how it goes. So we got to go back to the definition, and the definition tells us that this object has to be the unique continuous martingale equal to the Ito integral of indicate a function of 0 t evaluated at s times bs. So what's the definition of that Ito integral? It's the limit of an Ito integral of simple processes. So I'm going to exhibit a simple an H2 naught process that approximates the process bt, and that's going to be defined as fn being the sum j equals 0 to n minus 1 of bj over n times the indicator function of the interval that goes from j over n to j plus 1 over n. And then, that's a function of t and omega defined in this way. for almost every t in 0, 1, and omega in capital Omega. So my claim is that Fn is a approximation of the process Bt. So if I define F to be the map that sends t to Bt, then my claim is that Fn minus F in L2 norm goes to 0. Right? So I have an approximating sequence, and therefore the Ito integral of Fn is going to approximate this Ito integral that I'm trying to compute. Right, so that first we need to prove that claim. We need to prove that this is indeed a good approximation sequence, and what I did is like a left rectangle approximation from a Riemann point of view, right? I evaluated the process at the left endpoint of the interval over which I'm integrating. So in that way, this is an H2 naught process. This is adapted because t is always above j over n, and I'm having here something which is fj over n measurable. But does that approximate f in the appropriate topology? Well, let's find out. Let's compute. Should have said all of that, of course, is for every n in n. Let's compute the L2 norm of that. Maybe square it, keep things simple. So it's an L2 norm over the probability space and over 0, 1. And I'm looking at the sum j equal 0 to n minus 1 of b j over n of omega times this indicator function. And I'm subtracting to that b t of omega, and bt of omega is equal to bt on every single one of those intervals. So let's write it to keep it a little simpler as minus bt of omega times this in the indicator function of the interval jn to jn plus 1 over n of t squared, and then you do that dt and dp of omega. Now notice that all of these intervals are disjoint, so if you expand this square here, you're not going to get any cross term once you integrate, because the integral of a product of these two such thing is 0 unless j is equal to k, right? If you expand that to the sum of a j and a sum of a k. So what you get is that this is equal to the expectation. You can put all the sums outside now because of this orthogonality of the indicator functions, and you get an expectation, an integral, a bgn of omega. Sorry, if I write expectation, I should not write dp omega. That's better. I should not write my omegas. So expectation of bjn minus bt, which are random variable, squared times this integral j over n to j plus 1 over n indicator functions as a function of t. Okay, so now this expectation of bjn minus bt squared, we know what it is, right? Because increments of the Brownian are Gaussian distributed. So what we get here is t minus j of n. And then we're integrating between j of n and j plus 1 over n. And we integrating dt. And now this is a standard Riemann integral, which I can compute. And what do I get? I get j plus 1 over n minus j over n squared times 1/2. And this is equal to 1 upon n. So I get 1 upon n squared, and I'm summing that. This sum is over n terms. So I get n divided by 2n squared, which is 1 upon 2n. And the point is, well, this nicely goes to 0 as n goes to infinity. Okay, so Fn is an approximating sequence for f, and so the integral bs dbs of 0t is going to be the limit as n goes to infinity of the integral 0t fn of s dbs. And that's true for every t in 0, 1, and this limit is understood in the L2 sense, right? It's the limit for the L2 topology, L2 of omega topology. Right, so in order to compute what I want to compute and eventually prove that it's bt squared over 2 minus t over 2, I need to compute these Ito integrals of H20 processes and find out what their limits might be. So let's do that. So our definition of Fn is here, right? It's this left rectangle approximation. So I know precisely what this integral is, right? What is the integral from 0 to t of Fns dbs? It is the sum, j equals 0 to n minus 1 of bj upon n times the integral from 0 to 1 of the indicator function of 0t of s times the indicator function of j upon n to j plus 1 upon n of s dbs. Now, whenever t is below j upon n, I'm really integrating 0. So what I have here is the sum, j equals 0 up to some point knt of my bjn times bj plus 1 upon n minus bjn. And then I have the next term, the term corresponding to the j that is such that t is exactly between j upon n and j plus 1 upon n. And then I get b kn of t times bt minus kn plus 1 of t minus bt minus bkn of t plus 1, right? And where kn of t plus 1 is such that t is between kn of t plus 1 and kn of t plus 2. And this is a uniquely determined number, integer between 0 and n minus 1. All right, so this is the concrete expression from this integral I'm trying to compute. But now we want to try and relate that to the bt squared over 2 minus t over 2 that we are trying to obtain. And in order to do that, we're going to use the following property, right? We have to look at all sort of things that are of the form b something times that same thing minus another element of the Brownian. So here is a little remark, a little algebraic remark. 2bt times bs minus bt is always equal to bs squared minus bt squared minus bt minus bs squared. Right? You just compute it and you will check that this equality holds. So this algebraic property is what we're going to use to relate these sums that involves a Brown and the Brownian at the time times an increment of the Brownian to things like difference of the Brownian squared or difference of the Brownian all of that squared, which are things that we that are more related to the quadratic expression bt squared over 2 that we want to get. And so doing that tells us that, using this algebraic formula and applying it to the first part of the sum, we get 1/2 of the sum from j equals 0 to k and t of what? Of bj plus 1 upon n squared minus bj upon n squared. And that's great because it's going to be a telescoping sum. And then we get minus 1/2 of the sum from j equals 0 to kn of t of bj upon n minus bj plus 1 upon n, and all of that is squared. That's what we get from the sum part. And then we have the lone term, that term, and it gives us the same formula, 1/2 of actually, do I really need to do that? I don't even need to do that. I'm going to keep that last term as it is. So the last term is bkn of t plus 1 times bt minus bkn of t plus 1. Why do I keep the last term as it is? Because the last term really is an error term, right? The idea is that kn of t plus 1, as n goes to infinity, that's going to approach t. So by continuity, almost surely, of the Brownian, this term here is going to go to 0, at least almost surely. So this term here is going to eventually contribute, as I take limit as n goes to infinity, not contribute anything to the computation of this integral. This term here, well, this term is a telescoping sum. And computing that telescoping sum, I get bk n of t plus 1 divided by n. I forgot to divide by n here. Did I forget it here? Yes, I did. And so this is that squared minus b0 squared, but b0 is 0. So this just gives me 0 in my first telescoping sum. And then I've got a term here, kn of t, of bjn minus bj plus 1 upon n squared, and then I've got that last error term. So what is the idea here? As I send n to infinity, I expect this last term to go to 0. I expect this term, of course, to go to bt squared over 2, because knt plus 1 over n goes to t. And well, what about this term? That is really the interesting term. That's the term that's going to go to t over 2. So let's write that. So the idea is kn of t plus 1 divided by n goes to t as n goes to infinity. Okay, that's a fact. There's properties of numbers. I mean, k and t plus 1 upon n minus t. Well, let's write it like that straight away. That is always smaller than 1 upon n. So this is certainly going to 0 as n goes to infinity. Now, that means that by continuity of the Brownian, I expect, and I forgot an upon n here too, I expect, probably forgot it there too, I expect these terms to go to 0 as n goes to infinity, at least almost surely, by continuity of the Brownian. Now this is also going to go, at least almost surely, by continuity of the Brownian to bt squared over 2. And now what we really need to show is that this term here this term here goes to t as n goes to infinity. That's what we need to conclude the proof. So let's see how we prove these different things. And the way we're going to prove that last one, by the way, is subtract t to that and show that in an appropriate topology, this goes to 0 as n goes to infinity. So this would be an error term. This would be another error term that we have to show can be made arbitrarily small as n approaches infinity. Okay, so let us handle the easy terms first. So as we just mentioned, kn of t plus 1 upon n minus t, that's smaller than 1 upon t, so that goes to 0 as n goes to infinity. So by continuity of the Brownian trajectories, we have that b kn over t plus 1 divided by n squared tends to bt squared almost surely. All right. Now, do we have convergence in L2? Well, if I look at these objects square, I get this Brownian, this trajectory of the Brownian to the power 4. That's a Gaussian variable, so this expectation to the power 4 is going to be equal to 3 knt plus 1 over n squared. Doesn't really matter what that is. It's certainly smaller than 3 for all n. So these variables are uniformly in L2, and we've seen that this implies uniform integrability. So by uniform integrability, we have that the expectation of b knt plus 1 over n squared minus bt squared, and expectation of that squared to get the L2 norm squared has to go to 0 as n goes to infinity. So that's the first thing we had to prove. Now that gives the first term in the bt squared over 2 minus t over 2, it gives me the bt squared over 2. Now what about this error term at the end, which looks like b kn over t plus 1 divided by n times b kn over t plus 1 over n minus b of t? Does that go to 0 in L2 norm? Well, let's have a look. Let's compute the expectation of that squared. Now note that this is an increment of the Brownian. I can subtract b naught between 0 and knt plus 1 over n, and this is an increment of the Brownian on a disjoint interval, the interval between knt plus 1 over n and t. Therefore, by independence of increment of the Brownian, this expectation of a product is the product of the expectations. So expectation of that squared times expectation of this squared. All right, and now you know how to compute this expectation square because the Brownian increments are Gaussian distributed. So this is exactly equal to kn over t, knt plus 1 divided by n times t minus knt plus 1 divided by n. Now this goes to t as n goes to infinity, and this goes to 0 as n goes to infinity. Therefore, the entire thing goes to 0 as n goes to infinity. So it means the error term goes to 0 in L2 norm as n goes to infinity. Now, these were the two easy terms, and now we have to look at the harder term. So the harder term, let's call it yn, and it is defined as the sum from j equals 0 to kn of t of bj plus 1 over n minus bj over n, and then you square that. And what do we need to show? We need to show that in L2 norm, yn of t goes to t. So we need to show that yn of t minus t as n goes to 0, as n goes to infinity, goes to 0. And this will conclude the proof. So this term ynt is what we call the quadratic variation of the process. We'll see later on that it's part of a more general theory of quadratic variations of stochastic processes that will play a key role. They will be the correction terms in our analogues of the fundamental theorem of calculus. But let's have a little aside at this stage just to understand a little bit what's going on. What if instead of the Brownian, I was just using the function x goes to x like you do in Riemann integration? Then I would have yn of t equal the sum of j plus 1 over n minus j over n squared, j equals 0 to kn of t, and this would be equal to what? This would be equal to knt plus 1 times 1 upon n squared. But knt plus 1 upon n goes to t, and 1 upon n goes to 0. So this entire thing would be going to 0 as n goes to infinity. So in the deterministic case, what's going on is that the quadratic variation goes to 0 as n goes to infinity. So you don't pick up any term that involves a quadratic variation of whatever you're integrating against when you do Riemann integration. But in stochastic analysis, we will pick up those terms because we are going to see that y and t does not go to 0. In fact, it does go to t. And it has to do with the fact that the expectation of the squared of increment of the Brownian is equal to what? Well, it's equal to 1 upon n. So it's actually linear in the time variable as opposed to being quadratic. So the quadratic terms will play a role in our integration theory. That's the idea. But let's see that by hand on this concrete example. So the first thing is that, well, if I were to look just in expectation, right? If I were to hope for 1 second that yn could go to 0, I should look at the expectation of yn of t. And what is the expectation of yn of t? This is the sum j equals 0 to knt of this expectation of the increments of the Brownian. And this is the sum j equals 0 to kn of t of 1 upon n, right? As opposed to what I had on the other side, which was 1 upon n squared. And so this is equal to kn of t plus 1 divided by n. And as we've seen, this goes to t as n goes to infinity. Okay, so the expectation of yn of t is t, but does yn of t goes to t in L2 norm? So I need to compute the expectation of yn of t minus t squared. And what is that? Well, if t is the expectation of yn, then this is really the expectation of yn minus its expectation, and then I square that, which is by definition the variance of yn of t. And yn of t is given as a sum of random variables, right? So it's a sum of bj plus 1 upon n minus bj upon n. Now notice that, squared. Now notice that these variables are independent of each other, right? Because increments of the Brownian are independent. So by independence, the variance of a sum of independent variables is the sum of the variance of these independent variables. And so what we get here is the sum of the variances of bj plus 1 minus bjn squared. And what is that? Well, let's write it explicitly. It's a variance, so it's the expectation of this thing squared minus its expectation and then we square this. Right, so what do we get here? We get the sum from j equals 0 to kn of t of the expectation of, and now let's expand that square. So the first term is going to give me a bj plus 1 upon n minus bj upon n to the power 4. Then I get a minus 2 times the cross terms. And this expectation here of this squared is equal to 1 upon n, right? So this is 2 divided by n. And then I get plus this 1 upon n squared. So that gives me a 1 upon n squared. Very good. So what have we got? So we've got the sum j equals 0 to kn of t. The expectation of an increment to the fourth. Again, this is a n0 1 upon n Gaussian variable, normal variable. So this gives me a 3 times n squared. The second terms give me a minus 2 upon n times the expectation of the increment squared, which is 1 upon n. So I get a minus 2 upon n squared, and then I get a plus 1 upon n squared. So altogether, that's 4 minus 2 is 2. So I get 2 upon n times k n t plus 1 upon n. But this goes to t as n goes to infinity, and this goes to 0 as n goes to infinity. Therefore, the entire thing goes to 0 as n goes to infinity. Now, that is to say that yn of t goes to t. Therefore, the integral from 0 to t of bs dbs is equal to 1/2 of bt squared plus 0 minus 1/2 of the limit in L2 as n goes to infinity of yn of t, and we've just seen that this is t. So 1/2 bt squared minus t over 2 is the answer. And we've completed our first computation of a Ito integral by hand. Now you could do the same thing trying to integrate bs squared instead, and that's a possible exercise. It takes quite a lot of effort instead of an algebraic formula to expand the squares, to expand the bt times bt minus bs using this formula that gives the 1/2 and the difference of squares. You have to use a similar formula with cubes, and the algebra gets harder and you have extra error term to control, but you control them in the exact same way using formulas for the successive moments of a normally distributed random variable. Now, we're going to try to put that into a more general theory. As you can guess, this would be extremely difficult to compute Ito integrals by hand, exactly in the same way as it would be very difficult to compute Riemann integral by hand if we didn't have the fundamental theorem of calculus. So we need to build up towards a general theory, and that's going to be Ito's formula that gives us that. That includes a replacement for the fundamental theorem of calculus, and that tells you that this has to be the right answer. And we'll see that by having a general theory of quadratic expectations, so seeing what is the analog of yn in the general case, and what should it tend to as n goes to infinity in terms of what we're integrating. So that's what we're building towards, but we need a little bit more theory before we can get there. And the reason for that, it's because the appropriate context for Ito formula, but also in order to prove Ito formula, we need to have an Ito integration theory that goes a little bit beyond H2 processes and allows us to integrate any continuous function of the Brownian motion. And that's what we need to do next, extend our theory a little bit past H2 to a class of processes called L2 log processes that would include every continuous function of the Brownian. And then we'll find out that what we did in this particular example here, really approximating the Ito integral in a way that is very reminiscent of what we do in Riemann integration, we will be able to do that for general continuous function of the Brownian, thanks to the theory we're about to develop in the next part of the chapter.